An eigenfunction of the operator d square by dx square is psi is equal to e raised to 2x. Find the corresponding eigenvalue. We have studied the eigenvalue and eigenfunction. If an operator A operates on a function psi, then we get the same function multiplied by a constant, and this constant is called eigenvalue and this function is called eigenfunction. Similarly, here the operator is d square by dx square. Instead of a, we are substituting d square by dx square and the function is psi is equal to e raised to 2x. Then the equation is a psi can be written as a psi is equal to, instead of a, the operator is d square by dx square, d square by dx square, and the psi is here e raised to 2x. Then we get d by dx of 2 e raised to 2x, or it can be written as d by dx of e raised to 2x is, that is 4 e raised to 2x. That is a psi or d square by dx square e raised to 2x is equal to 4 e raised to 2x. Hence the eigenvalue is 4. And e raised to 2x is the eigenfunction and d square by dx square is the operator. And the next question is, find the expectation value x of the position of a particle trapped in a box L wide. So we have studied the expression for expectation value as, that is, in generally the expectation value for the position of the particle can be represented as x equal to integral minus infinity to plus infinity psi star x psi dx for a one dimension. And this expectation value is for a normalized wave function, because for a normalized wave function integral minus infinity to plus infinity psi star dx equal to 1. Here we are considering a normalized wave function. And the wave function for a particle which is trapped in a box of width L is given by, this psi is equal to root 2 by L sin n pi x by L. This is the normalized wave function for a particle which is trapped in a box of width L, and root 2 by L is the normalization constant. And here we are using this psi value as this one. Then the expectation value can be represented as, expectation value for the position of a particle x can be written as integral, the box width is L, so 0 to L, x psi square dx. Psi star can be written as psi square dx. And this equation will become, it is integral 0 to L x psi square is 2 by L sin square n pi x by L. Therefore 2 by L sin square n pi x by L into dx. Taking 2 by L outside, that is 2 by L integral 0 to L x sin square n pi x by L dx. And this equation is in the form sin square theta. We know that the sin square theta is 1 minus cos 2 theta by 2. That is sin square theta is 1 minus cos 2 theta by 2. Therefore, sin square n by x by L is 1 minus cos 2 n by x by L divided by 2. 2 by L integral 0 to L x 1 minus cos 2 n pi x by L the whole by 2 into dx. And this can be taken as 2 by L integral 0 to L. This can be taken into two different integral, that is x by 2 dx minus integral 0 to L x cos 2n pi x by L into dx. For the first term, 2 by L into integral 0 to L x by 2 dx minus, this is also the product of two terms, x and cos 2n by x by L. So we can again differentiate it, integrate by parts. First function is x, second function is cos 2n by x by L. Then we can derive in terms of, we can solve this in terms of the integration by parts. That is, the first function is x, the second function is cos 2n by x by L. First function into integral of the second, that is sin n by x by L, sin 2n by x by L divided by 2n pi by L minus integral of derivative of first x 1, then integral of the second sin 2n pi x by L divided by L into dx. And for the first term it is 2 by L into, this will come x dx, it is x square by 2, and applying the limit we get, that is x square by this 2 will be 4, that is 0 to L minus, this is x, that is 2n pi by L x divided by 2n pi sin 2n pi x by L 0 to L. Within the limit 0 to L, the sign of 2 pi multiple, it will be 0. Then this term will be 0. Because when substituting x equal to L, this will become sin multiple of 2n pi. And also in the third term, on integration this we get cos 2n pi x by L divided by 2n pi by L the whole square. This also on integration, and also when applying this limit we get cos 2n pi, it is 1, and cos 0 is 1, then 1 minus 1, this will also goes to 0, and these two terms will be 0. The remaining term is 2 by L, that is x square L square by 4, that is this will be 2 and L by 2. This is L by 2. That is probability of, find the expectation value, that is the average value of the position of a particle trapped in a box is given as the L by 2. That is, if L is the width of the box, then L by 2, that is the middle of the box. Then the third question is, a harmonic oscillator is in a ground state. What is the probability density? Where is the probability density maximum, and what is the value of maximum probability density? And we have studied the equation, the eigenfunction of a harmonic oscillator, that is general equation for a normalized wave function. Eigenfunction can be written as psi n y is equal to, we have studied the harmonic oscillator as psi n y is equal to m omega by h cut by the whole raised to 1 by 2 raised to n n factorial the whole raised to 1 by 2 hn by e raised to minus y square by 2, where this hn y is the Hermite polynomial and this y square is m omega by h cut into x square, and this is the general equation for the eigen function. And for the ground state is n is equal to 0. When n becomes 0, this equation is psi 0 is m omega by h cut by the whole raised to 1 by 2 1 by, when n is equal to 0, 2 raised to 0 0 factorial the whole raised to 1 by 2, that is m omega by h cut by the whole raised to 1 by 4, and this is hny, that is when n equal to 0 this will be 1 and e raised to minus y square by 2, that is y square is this one minus m omega by h cut divided by 2 into x square. This is the equation, m omega minus m omega by h cut 2h cut x square. This is the value of the ground state eigen function, m omega by h cut by the whole raised to 1 by 4 exponential e raised to minus m omega x square by 2h. And where is the probability density maximum? And we have the probability density p can be represented as px equal to psi star. Here it is psi 0 star. For the ground state it is psi 0 star. And when taking the square of this equation, that is m omega by h cut by the whole raised to 2 by 4 e raised to minus m omega by h cut square x square the whole square. Therefore the 2 and 2 will cancel. Here it will be 1 by 2, that is m omega by h cut by the whole raised to 1 by 2 exponential e raised to minus m omega x square by h cut. This is the equation, probability density. And the where is the probability density maximum? What is the value of maximum probability density? And the probability density p will be maximum at the point where the dp by dx equal to 0. It's a function of x. That is, the maximum will take place when at the point when dp by dx equal to 0. When this dp by dx equal to 0, this will becomes, that is m omega by h cut by all raised to 1 by 2. This is constant, and the constant into e raised to minus m omega x square, and that is it will be becomes, that is e raised to exponential minus m omega x square by h cut into the x square, this term, it is into minus 2x m omega by h cut. This will be 0. That is, we can rearrange this as m omega by h cut by the whole raised to 1 by 2 m omega divided by h cut minus m omega divided by h cut into 2x into exponential minus m omega x square by h cut is equal to 0. This is the equation. That is dp by dx equal to 0. That is, this term will be 0, these are a constant, or x will be 0. Therefore, the probability density is maximum at the point where x is equal to 0. That is, probability density is maximum at x equal to 0. Here at this point the probability density will be maximum, and we can calculate the maximum probability density. That is, the maximum probability density density, it is here P0. We are giving a notation as P0, and this will be the maximum probability density will be this value. This x is equal to 0. When x equal to 0, and this will terms goes to 1, and this is the value m omega by, that is m omega by h cut pi the whole raised to 1 by 2. This is the maximum value of the probability density.